Let us start chapter 8, 8.1, Relations on Sets. First of all, recall that if A and B are two sets, then a binary relation from A to B is a subset of the Cartesian product between A and B. Given an ordered pair, a point like x and y in the Cartesian product, we say that x is related to y by r. We write it as x is related to y by r if and only if x and y is a point in that relation. The term binary is the definition refers to the fact that the relation is a subset of Cartesian product of two sets. Because we focus on binary relations in this book, when we use the term relation by itself, we will mean binary relation. Let's go over some examples to see what's going on here. Suppose we want to define a relation from z to z. Remember that z is just the set of integers. And this relation is defined this way. M is related to n using E, or point M and n is in E if and only if m minus n is even. Question says, first of all, is 4 in relation with 0 through E? Is 2 in relation with 6 through E? Is 3 in relation with -3 through E? And also, is 5 in relation with 2 through E? Since we defined the relation this way, we have to find the subtraction between two elements. 4 minus 0 is 4, and we know that 4 is even. So 4 and 0 is a point in that relation. 2 minus 6 is -4. You get a negative even integer. So of course, it's even. It satisfies the condition. So 2 and 6 is a member of E. 3 minus -3 is 3 plus 3, which is 6. And we know that 6 is even. So 3 and -3 is also a point in that relation. 5 minus 2 is 3, which is not even. So these 3 points belong to relation E, but not the last point. Very well. B, list 5 integers that are related to 1 by E. So we can list any set of integers. 1 is related to 1 by E because 1 minus 1 is 0. And it's even. 3 is related to 1 by E because 3 minus 1 is 2 and 2 is even. 5 because 5 minus 1 is 4 and 4 is even. -1. -1 minus 1, which is -2. You get a negative even integer. So these numbers are satisfying the condition. And finally, you can take -3. -3 minus 1 is -4, and -4 is also even. Part C says, prove that if n is any odd integer, then for sure you can say that n and 1 is a member of E, or n is related to 1 through E. So let us use the definition to prove this. N is any odd integer. So n can be written as 2k plus 1, and k is any integer. Now, n minus 1 is 2k plus 1 minus 1. You can cancel out 1 and -1. The outcome is 2k. And by definition of an even integer, you know that 2k is even. So any odd integer, we just prove that any odd integer is related to 1 through E. Let us move on to the next page. Suppose X is the set of all elements A, B, C. power set of X, if you remember the definition, is the collection of all subsets of X. Empty set, X itself, subset with only one element, subsets with two elements. Now we define a relation like S from power set of X into Z, the collection of integers. We define it this way. We say that subset A is in relation with subset B through S if and only if set A has at least as many elements as B. So the cardinality of A must be greater than or equal to cardinality of B. Okay, question says, is subset AB related with subset BC? Is subset A is in relation with empty set? Is a subset including B and C in relation with subset including A, B, C, or just X itself? D, is the set including just one element, C, is in relation with subset including just one element, A? Very well. The cardinality of this set is 2, which is the same as the cardinality of the second set, so it satisfies the condition. These two sets have two elements, so these two sets are in relation with each other through S. The cardinality of set A is 1, and the cardinality of empty set is 0. Since 1 is greater than equal to 0, it means that B is true. Take a look at C. The cardinality of this set is 2, but the cardinality of X is 3. As you can see, 2 is not greater than or equal to 3, so this is no relation. And finally, the cardinality of this set is 1, the cardinality of the second set is 1, and they are equal to each other. Since you have equality, it means that set including C is in relation with set including just A. Next, suppose you have a relation R, which is defined as the collection of ordered pairs X and Y such that X is in A and Y is in B. You can define something that like a reverse relation with R and little exponent -1, which is just points, and X and Y are switched together. So the inverse relation is the collection of points Y and X such that Y is in B and X is in A. Remember that we use these two sets for one-to-one relations. X and Y is a point in R if and only if Y and X belongs to the inverse of R. Let's go over one example, see what's going on. Suppose A is a set including 2, 3, 4, B is a set including 2, 6, 8, and R, B, the relation divides from A to B. So X is in relation with Y if and only if X divides Y. Question says, form all ordered pairs that satisfying relation R and its inverse. Okay, 2 divides 2, 2 divides 6, 2 divides 8, so 2 divides 2, 2 divides 6, 2 divides 8, 3 divides 6, 4 divides 8. These are all the elements in the first relation. Now that you have your R, you can form the inverse of R by switching X and Y. 2 and 2, 6 and 2, 8 and 2, 6 and 3, 8 and 4. Very well. A relation on a set A is a relation from A to A. Remember that to visualize a relation, we can use a directed graph. For all points x and y in set A, there is an arrow from x to y if and only if x is in relation with y through R, or if and only if x and y is a point in relation R. Then you can write an arrow from x to y, directed arrow, and you call it R. If you have x and x as a point in R, you can use a loop connecting x to itself. Example. Suppose A is a set including 3, 4, 5, 6, 7, and 8, and we define a relation like R on A as follows. X is in relation with y, or x and y is a point in R if and only if 2 divides x minus y. Draw the directed graph of R. Okay, very well. So here you have 3, 4, 5, 6, 7, and 8. First of all, you can use a loop for each of these elements. Why is that? For example, take 3. 3 minus 3 is equal to 0, and 2 divides 0. So we have a loop for 3. The same for 4. 4 minus 4 is 0, 2 divides 0. So we have a loop on 4. So 2 divides 0, and this 0 is coming from 3 minus 3. 2 divides 4 minus 4. These are all zeros. 2 divides 5 minus 5, which is 0. 2 divides 6 minus 6, which is 0. 2 divides 7 minus 7, which is 0. 2 divides 8 minus 8, which is 0. That's why we have loop for each of these numbers. Okay. We can connect 3 to 5, also 5 to 3. Why is that? 2 divides 3 minus 5, that's obvious. 2 also divides 5 minus 3, which is 2. So for each of these pairs, we can check to see if the subtraction is an even number or not. As you can see, we do not connect 3 and 8 because 8 minus 3 or 3 minus 8, both of them are odd numbers, not even numbers. That's how we form our directed graph. Very well. Let R be a relation on set A. We say that R is reflexive if and only if x belongs to A and x is in relation with x itself. So x and x as a point belongs to relation R. R is called symmetric relation if and only if for all x and y in A, if x is in relation with y, then you can conclude y is also in relation with x. So if x and y is in R, it means that if x is connected to y with an arrow, then you can conclude that y is in relation with x. So you have an arrow connecting y to x as well. R is called transitive if and only if for any 3 values, numbers, objects in set A, if x is in relation with y is in relation with z, then you can conclude that x is in relation with z. So if you have x connected to y, also you have y connected to z, then you can conclude that X is also connected to Z. So equivalently, you can just use points, X and X, X and Y, Y and X, X and Y, Y and Z, and X and Z. Let's go over one example, see what's going on here. Let A be the set including 0, 1, 2, 3, and we define the following relations on set A. A says, is R reflexive, symmetric, transitive? Okay, let's check to see what's going on here. If R is reflexive, it means that 0 and 0, 1 and 1, 2 and 2, 3 and 3 are members of R. So this is true. R is reflexive. Is it symmetric? Okay. 0 is connected to 1. 1 is also connected to 0. 0 is connected to 3. 3 is connected to 0. What else do we have? So if you check each of these points, you can actually see they are connected together. You can form a directed graph for each of these and actually see what's going on. So you have 0, you have 1, you have 2, and you have 3. For each of them, you have a loop. That's why it is reflexive. Okay, 0 is connected to 1. 1 is connected to 0. 0 is connected to 3. 3 is connected to 0. What else do we have? That's it. Okay. Is this symmetric? Of course. If X is connected to Y, Y is also connected to X, and so on. There is no relation between 3 and 2, so we're not worried about 2 and 3. So it is symmetric. Do we have a transitive relation here? 1 is connected to 0, 0 is connected to 3. Do we have a connection between 1 and 3? As you can see, 1 is not connected to 3, so it is not transitive. Now let us form S, 0, 1, so 0, 1, 2 and 3, 0 and 0. Okay, we only have one loop here. Then 0 is connected to 2. Then you have 0 connected to 3. Then you have 2 connected to 3. First of all, this relation is not reflexive because you do not have loops for 2 and 3. What about symmetric? Very well, we don't have double arrows for these, so it's not symmetric. Transitive, okay. 0 is connected to 3. 3 is not connected to 2, so there is nothing here. 0 is connected to 2. 2 is connected to 3. And 0 is connected to 3, so it is transitive. You only check the connections, the relations that exist here. We do not care about relation between 0 and 1. There is no arrow here, so there is no point checking this to be transitive or not. Let's take a look at T. T says you have 0, 1, 2, 3. There is no loop. 0 is connected to 1, and 2 is connected to 3. Very well. This is not reflexive. You don't have loops. It's not symmetric. 0 is connected to 1, but 1 is not connected to 0. Is it transitive? Okay. 0 is connected to 1. 1 is not connected to anything, so there is nothing to check here. 2 is connected to 3. 3 is not connected to anything, so there is nothing to check here, so it is transitive. Example, properties of equality. Suppose we define a relation like R on R, the set of all real numbers. Note the difference between these two as follows. X is in relation with Y through R if and only if they are equal to each other. Question says, is this relation reflexive, symmetric, or transitive? Okay, first of all, this relation is reflexive. Why is that? Any number is equal to itself. So for any random x, any random real number, x is equal to x. 1 is equal to 1, 2 is equal to 2, 3 is equal to 3, and so on. So the first condition is met. Second condition, if x is equal to y, then for sure you can say that y is equal to x. It's like writing it this way. X is equal to 2. You can also say that 2 is equal to x. So it is symmetric. And also it's transitive. If x is equal to y and y is equal to 2, for sure you can conclude that x is equal to 2. So the relation is transitive as well. If a relation is reflexive, symmetric, and transitive, we call it an equivalence relation. Let us continue. Consider the properties of less than. Suppose you have R as the set of all real numbers and you define a relation on R. We define it this way. We say that x is in relation with y if and only if x is less than y. Question says, check to see if it's reflexive, symmetric, or transitive. First of all, it's not a reflexive relation. Why is that? 1 is not less than 1. 2 is not less than 2. These are not correct. Is it symmetric? Very well. We know that 0 is less than 1, but can you say 1 is less than 0? It's not true. So it is not symmetric relation. But how about transitive? If x is less than y and y is less than z, for sure you can conclude that x is less than z. Like saying that 1 is less than 2, 2 is less than 3, so you can conclude that 1 is less than 3. Of course it is true. So it is transitive. Let's see, what do we have? Very well, congruence module 3. Let us define a relation like T and Z as follows. We say that M is in relation with N through T if and only if 3 divides M minus N. Check to see if this relation, which we call congruence mod 3, is reflexive or symmetric or transitive. First of all, this is an equivalence relation. It means that for sure it is reflexive, symmetric, and transitive. We can prove it. Of course, if M is equal to N, 3 divides M minus N, which is 0. That's for reflexive. That's obvious. For transitive, for symmetric, let's go over symmetric first. Suppose 3 divides M minus N. Your goal is to show that 3 divides N minus M. But this is easy. Since 3 divides M minus N, then you can conclude that M minus N is equal to 3K for K as an integer. Okay, now suppose we multiply both sides by negative sign, you get N minus M equals to 3 times a new integer, negative K, which is L. So 3 divides N minus M. So we proved that this relation is symmetric. For transitive, suppose 3 divides n minus m and 3 divides m minus, let's see, minus t. Your goal is to show that 3 divides n minus t. Okay, this is not that hard. Since 3 divides n minus m can be written as 3k sub 1. Since 3 divides m minus t can be written as 3 times k sub 2. If you add these together, you can cancel out m and minus m. You get n minus t equals to 3k1 plus 3k2, which is a new integer, and it has factor 3. So n minus t is 3k sub 3. So 3 divides n minus t. So we just proved that congruence mod 3 is an equivalence relation. 8.3 Equivalence relations. Given a partition of a set A, the relation induced by the partition R is defined as follows. We say that X is in relation with Y through R if and only if there is a subset A sub I of the partition such that X and Y are in that partition. First of all, remember that for a partition of set A, it includes subsets of set A that have nothing in common. A sub 1, A sub 2, A sub 3, A sub 4, and so on. So if you take the union of these elements, A1, A2, A3, and so on, it's equal to A, and the intersection is equal to empty set. A2 has no intersection with A3, and so on. That's what we call a partition. So if you have a partition on a set, that partition actually induced a relation. This relation, let us call it R, is defined this way. We say that X and Y are members of relation R if and only if we can have one of these subsets such that X and Y are both in that subset, X and Y. Let's go over one example to see what's going on, to feel comfortable about this. Suppose set A is defined as a set including 0, 1, 2, 3, and 4. Suppose you have the following partition. These are subsets of set A. The union is equal to A, and there is no intersection between these 3 sets. So these 3 sets satisfy the definition of a partition. Okay, question says find the relation R induced by this partition. Let us start by working with the first element in this partition, which is subset including 0, 3, and 4. Okay, 0 is in relation with 3. Of course, they are both a member of the same set. So you can say that, hey, 0 and 3 as a point belong to R. What about 3 and 0? Of course, they both are in this subset. So you can say that 3 and 0 are a member of relation R. What about 0 and 4? Of course, you can see 0 and 4 here. What about 4 and 0? Of course. 3 and 4, yes. 4 and 3, yes. So as you can see, you have a relation here. That relation is induced by partition. You can also check to see If 0 is in relation with 0, of course. We don't have any repetition in a set, so we don't write 0, comma 0. We just write 0. 3 is in relation with 3, of course, because 3, comma 3 belongs to the set. Because we don't write repetition in a set, we just assume we have one unique element. 4 and 4, of course. Now let us take the second element in this partition, which is set including 1. Okay, take a look at this. This subset has only one element. If you take 1 in that set, 1 is in relation with 1. Of course, 1 and 1 is a member of that relation. And finally, you have a set including just 2. Is 2 and 2 a member of R? Of course, because 2, comma 2 or just 2 itself belong to the same set. So we can just take all of these elements, list them together, and define a relation which is induced by partition. 0, 0, 0, 3, 3, 0, 0, 4, 4, 0, 3, 4, 4, 3, 0, 0, 3, 3, 4, 4, 1 and 1, 2 and 2. Very well, let's see what's next. Okay, we have a theorem here. We have a theorem here. It says, let A be a set with a partition and R be a relation induced by that partition. Then this relation is reflexive, symmetric, and transitive. It's actually an equivalence relation. We need to show that for any two elements, if those elements are actually the same thing, x and x, you can find one subset of A that actually includes those elements. So suppose you have set A and you are just partitioning that set using subsets. There is no intersection between these sets, and it continues. A sub 1, A sub 2, A sub 3, A sub 4, and so on. So, of course, if X belongs to one of these subsets, X and X is in relation with itself. We cannot change this, the position of X. So X and X must belong to the same subset. Now suppose X and Y are in one of these subsets. You want to show that Y and X is also in that subset. Suppose not. Suppose Y and X, for example, is in A sub 3. So X and Y, for simplicity, suppose X and Y is in A sub 3, but Y and X belongs to A sub 4. What's the meaning of that? It means that A sub 3 intersection A sub 4 is not empty. Then it contradicts the definition of a partition, of being a partition. So there is no way the same member, X and Y, and its inverse are in two different subsets. So definitely it is symmetric. And finally, for transitive, suppose X and Y, both of them are in a subset like A sub I, and Y and Z belongs to the same subset. We want to show that x and z is also in A sub I. Again, suppose not. Proof by contradiction. Suppose not. And x and z, for example, is in any other subset. So you can say that, hey, suppose xy is in A sub 3 and yz is in A sub 3, then x and z is in A sub 4, for example. What could go wrong? We know that x and y is a member of A sub 3. Y and z is also a member of A sub 3. Okay, now you have a member like z or x, which is in A sub 4. What's the meaning of that? It means that the intersection between A sub 3 and A sub 4 is not empty. Again, it contradicts the definition of being a partition. Very well. Definition. Let A be a set and R is a relation on A. R is equivalence relation if and only if R is reflexive, symmetric, and transitive. One of the important equivalence relations is congruence mod D. So we say that M is congruent to N mod D if and only if D divides their difference. Remember that if D divides the difference, then M minus N can be written as D times K. So M can be written as N plus D times K. Quotient remainder theorem. Example, let us evaluate some congruence relations here. 5 divides 12 minus 7, of course. 4 divides 6 minus 8. It's asking if 4 divides 14. Of course not. 7 divides 0. Yes. So you just need to check to see if the mod, whatever it is, divides the difference between left-hand side and right-hand side. Example, an equivalence relation on a set of subsets. Suppose X is the set of all non-empty subsets of 1, 2, 3. So X is just the set of all subsets, not including empty set. Or you can say that, hey, I have power set of X, power set of 1, 2, 3, minus the empty set. They are equivalent to each other. Question says, define a relation like R on X as follows, and show that that relation is an equivalence relation. Okay, this relation says A is in relation with B through R if and only if at least the least element of A equals the least element of B. Okay, perfect. Let us show that reflexivity. R is reflexive. Why is that? Okay, take two subsets, in this case that we are showing reflexivity, A and B must be the same, and A is non-empty. Why is that? Because A belongs to X, and X includes all non-empty subsets of 1, 2, 3. For sure, you know that A is non-empty. Then, the least element of A is of course equal to the least element of A itself. There is nothing to prove here. Let us show that R is symmetric. Again, suppose we take two different subsets, A and B, from the set 1, 2, 3, and the least element of A is equal to the least element of B. Okay, it's obvious that the least element of B must be equal to the least element of A. There is no other way. You can consider it this way. Suppose I take these two subsets, 1, 1, and 3. The least element of this set is 1. The least element of this set is also 1. So the least element of A is equal to the least element of B, and also the least element of B is the same as the least element of A. The same discussion for transitive. If the least element of A is the same as the least element of B, and the least element of B is the same as least element of C, for sure you can conclude that the least element of A is the same as least element of C. Let's think about it this way. Take set 2, take set 2 and 3, take set 1 and 2. This is your A, this is your B, this is your C. The least element of set A is 2, which is the same as the least element of set B. The least element of set B, which is 2, is the same as the least element of C. Okay, let me change this guy because the least element of this set is not 2. Okay, we need to change C. So we have a correct set, 1, 2, 3. Okay, shall we repeat these two? These are just subsets. Maybe we can just repeat these two. Okay. The least element of C is also 2. So as you can see, the least element of A is the same as the least element of C. Now that we define an equivalence relation, we can take representatives of those relations and define something that we call equivalence class. So as usual, we take a set. Suppose you have set A, and you define an equivalence relation like R on A. Then for each element A in A, we can define equivalence class of A, which is the set of all those elements in A that are in relation with set elements in the set A. The notation that we use is bracket A, close the bracket, equals to the set of all elements in A such that X is in relation with A itself in set A. Let's go over one example, see what's going on here. Suppose you have set A equals to 0, 1, 2, 3, 4. Define a relation on A this way. That relation includes 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, which is reflexive. Then we include 0, 4, 4, 0. We include, let's see, 1, 3, 3, 1 to make sure we have a symmetric here, and we include, okay, that's it. We don't need to include anything else. We're not worried about transitive relation. We can also graph this relation. Then the question says, find the distinct equivalence classes of R. First of all, you have to list all of the elements in set A. Set A includes 0, so equivalence class of the first element. Open the bracket, close the bracket, put 0 is the set of all elements in set A such that X is in relation with 0. So X is in relation with 0. We have to check all these points in R. What numbers are in relation with 0? So the second member is 0. X can be 0. X can be 4. So equivalence class of 0 is the set including 0 and 4. We're done with the equivalence class of the first element. equivalence class of the second element. Open bracket, close bracket, 1 is the set of all elements in A such that X is in relation with 1. Again, we have to check R. The second element is 1. 1 is in relation with 1. 3 is in relation with 1. 3. What about equivalence class of 2? We're looking for all values in A such that those elements are in relation with 2. The second member is 2. The only pair here is 2 and 2. So 2 is the only element that is in relation with 2. Very well, we can continue this process, find equivalence class for 3, equivalence class for 4. And that's how we get distinct equivalence classes for this relation. Next, equivalence classes of the identity relation. Identity relation and equality are the same thing. So suppose we define a relation on set A as follows. X is in relation with Y if and only if X is equal to Y. This relation is an equivalence relation. We can define the equivalence classes of elements of R this way. So open bracket, close the bracket, including a member, a random member in A. Using the definition, it's the set of all elements in A such that X is in relation with A. Very well. What elements are in relation with A? This relation is defined as equality. The only element that is in relation with A or equal to A must be A itself. So this equivalence class has only one member, which is A itself. Equivalence class of A is the set including A. Okay, lemma. Suppose A is a set, R is an equivalence relation on A, and A and B are two elements in A. If A is in relation with B, for sure you can say that equivalence class of A is the same as equivalence class of B. Very well. To show that we have equality, we need to show that left-hand side is a subset of right-hand side, and right-hand side is a subset of left-hand side. Very well. First of all, let's show that left-hand side is a subset of right-hand side. So we take a random element in equivalence class of A on the left-hand side, and we show that that element eventually lands in the set of elements that are in relation with B. So X belongs to equivalence class of A. Remember the definition. It's the collection of all elements like X such that X is in relation with A. X is in relation with A. Okay, at the same time, we know that A is in relation with B. So let us use the fact that we learned in this lemma. X is in relation with A is in relation with B, and we have an equivalence relation because of transitive property of R. X is in relation with B. What's the meaning of that? It means that X belongs to equivalence class of B. With the same argument, you can show that B, equivalence class of B, is a subset of equivalence class of A, and that's how we prove equality between two equivalence classes. Very well. Another lemma here for you. It says, suppose A is a set, R is an equivalence relation on A, and A and B are elements of A, then either equivalence class of A is the same as equivalence class of B, or there is no intersection between these two. Let us prove this lemma. Suppose A is a set and R is an equivalence relation on A. A and B are two elements in A. Suppose the intersection is not empty. Our goal is to show that they must be equal to each other. When the intersection is not empty, it means that you can find at least one element like x, which belongs to the intersection. So x is in the first set, and x belongs to the second set. Using the definition of equivalence classes, x is in relation with A, also x is in relation with B. At the same time, we know that R is an equivalence relation. It's symmetric. So x is in relation with A, or A is in relation with x, and x is in relation with B. It gives you the result that A is in relation with B. Therefore, by using the previous lemma, equivalence class of A must be equal to the equivalence class of B. And finally, theorem, the partition induced by an equivalence relation. If A is a set and R is an equivalence relation on A, then the distinct equivalence classes of R form a partition of A. That is, it means that the union of equivalence classes is all of A, and the intersection of any two distinct classes is empty. Modular arithmetic and Z sub n. Theorem. Suppose A, B, and n are integers. Suppose n is greater than 1. Then the following statements are all equivalent to each other. It means that 1 is equivalent to 2, 1 is equivalent to 3, 1 is equivalent to 4, 1 is equivalent to 5, and you can work with pairs of these and show that they are the same thing. N divides the difference between A and B. It means that if you follow the definition, A is congruent B mod n, or if we use the quotient remainder theorem, A is equal to B plus Kn. We can also say that A and B have the same remainder when divided by n, or A mod n is the same as B mod n. We can prove this theorem purely by using the definition. Suppose you take 1 and you want to prove 2. N divides A minus B. You want to show that A is congruent B mod n. Perfect. By definition of congruence modulo n, we definitely see that A minus B is equal to nk. So A is equal to B plus nk. So as you can see, A is congruent B mod n. N divides A minus B. We can take 2 and start proving 3, which is officially just using the definition, and so forth. Example, verifying a modular congruence. Verify that 7 divides the difference between 235 and 53. Very well, 235 minus 53 is 182, and 182 has factor 7. So since 7 divides right-hand side, 7 divides the left-hand side, and we just proved that 7 divides the difference between these two elements. So 235 is congruent with 53 mod 7. Definition. Given integers like a and n, such that n is greater than 1, the residue of a modulo n is a mod n. The non-negative remainder obtained when a is divided by n. mod operator, as I mentioned before in Python, for mod operator we use %. Okay, after doing the division between these two numbers, we get numbers either remainder 0 or remainder 1 or remainder 2 or remainder n minus 1, which form a complete set of residues module n. To reduce a number mod n, it means that to replace it by its residue mod n. If m modulus n greater than 1 is fixed, a discussion and an integer a is given, the word module n are often dropped and we just say that the residue of a. Very well. Theorem, congruence mod n, which is an equivalence relation. Suppose you have n is an integer greater than 1. Congruence mod n is an equivalence relation on the set of all integers. Then the distinct equivalence classes of the relation are the sets, including the remainder 0, set including remainder 1. Remember that these are equivalence classes. Equivalence class of 2 and equivalence class of n minus 1. As usual, equivalence class of A is the set of all elements in Z such that n divides the difference between M and A. So in another word, you can write equivalence class of A as the set of all elements, all integers, such that M is equal to A plus Kn for some integer like K. Let's take a look at the proof. So suppose n is any integer greater than 1. We want to show that the congruence mod n is an equivalence relation. So our goal is to show that it's reflexive, symmetric, and transitive. To show that it's reflexive, nothing actually needs to be done. If you take the exact same element, A, of course n divides A minus A, which is 0. So A is congruent A mod n. For symmetric, we can just use the direct definition. Suppose A is congruent B mod n. We want to show that B also congruent A mod n. When you say that A is congruent B mod n, it means that n divides A minus B, or A minus B is equal to nk, so B minus A is equal to nl. So, as you can see, B is congruent A mod n. The same thing for transitivity. If n divides A minus B and n divides B minus C, for sure you can say that n divides A minus C. Direct definition. So we just proved that congruence mod n is an equivalence relation. This is a relation and it is symmetric, reflexive, and transitive. Let's see what's next. Okay, theorem, modular arithmetic. Suppose A, B, C, D, and n are integers, n is greater than 1. Suppose A is congruent with C mod n divides A minus C. Also, B is congruent D mod n divides B minus D. Then you have the following. The sum of A and B is congruent with the sum of C and D mod n. It means that n divides a plus b minus c plus d. The difference between a and b is congruent with the difference between c and d mod n. So n divides a minus b minus c minus d. If you multiply AB, then it's congruent with the product of CD mod n. So n divides AB minus CD. And finally, a to the m is also congruent with c to the m mod n, or n divides a to the m minus c to the m for any positive integers. Proof is coming directly from the definition of congruence. Let's go over one example. So we know that 4 divides 55 minus 3. We also know that 4 divides 26 minus 2. So if you add 55 and 26, it's congruent with the sum of 3 and 2. It means that 4 divides the difference between these two numbers. Okay, let's take a look at it. We're going to show that 4 divides 81 minus 5. Just do the subtraction. You get 76. So of course it has factor 4. What if we subtract these two? 55 minus 26. Is this going to be congruent to 3 minus 2 mod 4? It means that does 4 divide the difference between these two numbers? The difference between 55 and 26, the difference between 3 and 2. So, of course, 4 divides 29 minus 1. What if we multiply these two numbers? 55 and 26, is it congruent with 3 times 2 mod 4? Does 4 divide 1430 minus 6? Of course. And finally, if I raise both sides to 2, 3, 4, 5, any positive integer, it's going to be divisible by 4, the difference. Okay. Z sub n, the integers mod n. We can now define z sub n. For any integer n greater than 1, z sub n is the set of all distinct equivalence classes for congruence mod n. So we take all of these equivalence classes and we say, hey, this is z sub n. Again, remember that equivalence class of A is the set of all elements in set like A, such that X is in relation with A. Definition of a binary operator. Suppose you have set S, a binary operator star on S is a function that maps a two-dimensional space into a one-dimensional space. For any two elements in S, this binary operation takes X and Y and maps it to X star Y. So this is your star operator, binary operator, S cross S to S. It takes X and Y and it maps it to X star Y. binary operation. Very well. A subset A of S is said to be closed under the operation star, binary operation star, if and only if you take any two elements in A, the outcome A star B is also a member of A. Let's go over one example to see what's going on. If Z is given, the set of all integers, is this closed under subtraction? It means that if I take any two random elements from Z, if I find the subtraction between these two elements, is this going to be in Z? Of course, the subtraction between two integers is also an integer. What if I change the set to be just positive integers? Is this again closed under subtraction? Okay, suppose I take 2 and 1 in Z. 2 minus 1 is in Z. 1 minus 2 is in Z as well. But what about 1 minus 2 in Z plus? The outcome is going to be -1, which is not in the set of positive integers. So it's not closed under subtraction. Is Z closed under division? Of course not. Okay, the following two binary operations are defined on the set Z sub n. We call one of them addition and the other one multiplication. So we define addition this way. The sum of two equivalence classes is the same as equivalence class of their sum, and the product of equivalence classes is the same as equivalence class of their products. We have a theorem here. Given any equivalence classes A, B, C, and D in Z sub n, where A, B, C, and D are just integers, if equivalence class of A is equal to equivalence class of C, and equivalence class of B is equal to equivalence class of D, then equivalence class of A plus equivalence class of B is the same as equivalence class of C plus equivalence class of D. We have the same thing for the multiplication. Equivalence class of A multiplied by equivalence class of B is the same as equivalence class of C times equivalence class of D. Proof. Okay, perfect. So suppose you have these four equivalence classes and A, B, C, D are integers, and suppose you have the condition. Very well. Equivalence class of A is equal to equivalence class of C. It means that n divides A minus C. Equivalence class of B is the same as equivalence class of D. It means that n divides B minus D. We can use the properties and lemma that we learned before. You can just add A and B, which we know that is congruent with the sum of C and D mod n. Or you can just use directly the definition and show that n divides the sum and the difference between these two sums. Therefore, equivalence class of A plus B is equal to equivalence class of C plus D. Very well. And the last definition, suppose S is a set with two binary operations, addition and multiplication. S is called a commutative ring if and only if the following properties or hold. First of all, addition is commutative. A plus B is the same as B plus A. Also, multiplication is commutative. A times B is equal to B times A. For both of these operations, you have associative property. A plus B plus C is the same as A plus B plus C. And A times B times C is the same as A times B times C. We have distributive property. You can distribute multiplication over addition. A times B plus C is AB plus AC. You also have identity for addition and identity for multiplication. The identity for addition is actually 0, A plus 0 is A, and the identity for multiplication is nothing but 1. A times 1 is equal to A. And finally, you have additive inverse for element A. For any element like A in S, for sure you can find another element like B, which is the opposite of A. We satisfy the condition that the sum is equal to 0. Element B is called the additive inverse of A.